So welcome everyone to this year's DrawingLayer talk. So this year I wanted to concentrate not to take on a high level about the primitive stuff and all this again and what is happening in the background to prepare all the needed data for the rendering of the edit views. This time I just wanted to show you 4 concrete examples which happened about the last year, which are in the product and have led to some good speed ups, and they describe pretty well where the problems are currently, and seeing how to solve them can help to understand how to use the current techniques to be able to solve such problems. So just let's start with one of my favorite bugs in the last time, the squirrel bug. So the big problem is that we have an SVG import which we got from an external customer. I think it was Munich. They used a SVG graphic called Squirrel in very small form, just in writer, and this document just didn't work. And the reason was really this SVG graphic. It's pretty big, half a megabyte, and the reason it works so slow is it contains 5 SVG patterns, each containing 440 polygons by itself, just to describe simple points, but 440 and 5 of those patterns in the SVG file. And these patterns are used with texture repeat to fill just polygons. And this multiplies with the 440 polygons, so you had millions of simple polygons just to define the graphic in end effect when it was all folded up and prepared for rendering. So before render decomposes pattern and processes, it transformed 1,000 times. So there is actually some reuse when the pattern is prepared as primitive. It is not copied or something. It's just a reference, because a primitive is a new API object. So that is not even the problem. But the problem is that really all of these polygons get transformed system-dependent to the system-dependent form and have to be rendered in each for its own. And afterwards I just decided, don't do that, just pre-render one of the tiles as RGBA and render it as bitmap. So this of course works too, but you have to do some fine-tuning, because quality of pre-rendered bitmaps is of course not as good, so you have to take care for the output target. Is it output target bitmap like screen, or do you have meta file or PDF export or printing? Then you should avoid to do that, of course. And only up to a specified zoom level, because when you zoom deeply in, you automatically don't have the problem, because only a few of the tiles are rendered. So you can just go the way to use a higher quality. So the original approach had a high quality, but had speed problems when all of the stuff was shown. And this is a good example how you can optimize stuff using the primitives. You can just react inside the primitive decomposition, or you have the alternative to do it in the active renderer. And in the renderer, when you get to pattern repeat primitive, you can just say, when you know the concrete resolution, what will I do to get this graphic out as fast as possible? And I have this here. This is this squirrel which you have now, and now you can really zoom in. It's still not extremely fast, but you can see, you can at least scroll in it, and when you go really deeply into it, you see these patterns. So these patterns are not really useful in the end effect because they are more or less just used to make some gray tone. But of course you cannot ignore the definition of the underlying SVG, so you have to render them somehow. It would look different. So this was solved and is much faster now, as you see. So maybe after each of the examples, I have 4 of them. Maybe if you have questions to this example, make a short break. Okay, fine. Let's go to the next one. We have a problem with fat line drawing on Linux. Fat line is every line may it be just a straight simple line with 2 points, or may it be a Bézier curve when the line thickness is not on 0, which means in the office to have independent from the zooming, you have a 1 pixel line, which is, by the way, not provided by other office programs and just for historical reasons. So most of the problems come from OLED charts which have such fat lines, and in X11 there's simply no support for filled polypolygons, which are the result when you decompose the fat line, and of course no direct fat line support. So the problem is only on Linux, but with Cairo there is a solution now, and before the optimization the polypolygons had to be decomposed to trapezoids in full quality every time, no buffering, and this is of course pretty slow. And after the optimization I used Cairo, the direct fat line Cairo renderer, because I made measurements to decide what to do, and this is just the best way to do it. I also tried before to buffer the trapezoidation completely, but this has a bad memory overhead. So Cairo is just the way to go in here for the moment. In long term, we really need better support to draw in some way lines with some line thickness in just 1 color much better on Linux. We don't have a good solution today. I think what Quaylen was just talking about may help to get in the right direction, but what we really need is renderer, a basic renderer for the edit views, which is using that stuff that Quaylen is now offering. And I hope we get this together, because we can make huge steps forward when we do that. Questions to this example, maybe? By the way, this example also has the problems that geometry information has to come somehow from the 2D charts to the edit view at all. So there's a bridge now which directly uses the primitive representation. Before that, there were even meter files used for that. So I don't show the previous example live because loading that chart takes a long time. Maybe when we have some time left I can show later. So refactor 3D renderer to use multithreading. This is one thing I wanted to do for years and never found the time to do it. Because the 3D visualization is a 2D primitive which decomposes the 3D primitive content to RGBA bitmap, which is then painted. Due to supporting many systems, we need a fallback software renderer implementation to show all the 3D stuff. And up to today, unfortunately, the fallback software renderer is the only renderer for our 3D representations. So 3D is not overused in the office, but from time to time it gets used, and it would be nice to again use the stuff Quaylen was doing the last time to maybe at least get one day a direct hardware renderer for the 3D stuff. Would be no problem. You can just implement a primitive renderer which converts the 3D primitive geometry definition completely to this RGBA bitmap, so just a replacement for this fallback renderer. But the fallback renderer will still be needed even in the future. You never know where the office is running and if you have something like OpenGL available. So we always need a good fallback, and you also need a fallback for PDF rendering or something. There's no way to get OpenGL to render bitmaps in 1200 dpi when you want to print something in high quality or something. It's bitmap data. So before 2D primitive creates view-dependent RGBR in its decomposition, already intelligent buffering, but single-threaded. Already intelligent buffering means the fallback 3D software renderer is capable of just rendering parts of the 2D scene, and it takes into account if you zoomed in or out and which part can be reused. And even if you just zoom slightly in up to a difference of 25 or 50%, I'm not sure, I have to look in the source, it even avoids re-rendering and goes on bitmap scaling and stuff like that. So this is already pretty much optimized, and the interesting thing is this is all done inside of this one single primitive for a 3D representation. It's a 2D primitive for 3D scene representation. And all these optimizations and rendering and how to react on it can either be done in the renderer, if the renderer is the screen target, or directly in the decomposition, which is offered from the primitive. So there's even a choice. It's dynamic to do. So luckily there was already a thread pool in the office when I looked how I could parallelize that. And first it was hard to use it because it was a global thread pool, and of course it makes only sense to use the global instance of it. You could instantiate your own one, but of course makes no sense when you want to share your work with all existing CPUs. Luckily this was optimized so that you could wait exactly for the tasks you were scheduling yourself in your parallelization, and not for all tasks which could break other mechanisms in the office. So after that, I pretty rough parallelized rendering did work pretty well and brought some really good success. So now really when you have 8 cores may be used, and you can use much bigger 3D objects than before. For example, when you have something like this in the software renderer, this is nothing I would try to do with older Office versions. This simply will take minutes to, not minutes, but much longer to render. And in the current version, you can see it uses fat lines, and even with fat lines, you get a pretty decent reaction now when you are zooming or working with the graphic stuff. So this is much better response, and this is still the software renderer. Don't forget that, no hardware involved, and it's a software renderer which even does anti-aliasing with oversampling, so that you don't get some hard edges or something. So this is a big success, and you can see here that really the 3D renderer was using for short times a lot of the CPUs. Questions for this optimization? It shows again what you can really do using the primitives we have, and where you can go in between and do your optimizations. So, and hopefully when we get these CPUs with 32 cores or something, we heard about, it will get even faster. But it's still the software fallback, so we should really find some time or sponsoring or someone willing to do hardware 3D renderers. So the last example is more intelligent handling of animated GIFs. That's a problem and a bug Quaylen first found and roughly fixed by just on demand creating the GIF frames. Because with huge GIFs, there was an example GIF which was playing for 8 minutes or something, extremely crazy big stuff, and of course the office was breaking completely because Footprint did not handle this, because up to then the office was importing the GIF completely. The GIF was rendered into the single pictures as preparation, and the single pictures were put in an animated switch primitive, and it were, in this case, it were 800 or something of them, all pre-rendered as RGBA images and stored in this primitive. So for small GIFs this works perfectly, and all the images are pre-rendered, and you have a wonderful performance and no problems. And the reason this was done is that for the first time in the office history we were able to have multiple GIFs on one screen with overlapping and working animation stuff. But for this big fat GIF image we had just to do something more intelligent. And afterwards a specialization in animated switch primitive again. The solution is to directly do something inside the primitive which was hosting all the sub-level data and add some intelligence at that spot. So now it's holding, it's looking how much data it's holding, how many frames there are. Does it allow itself to use the pre-rendering? Does it buffer or not? How much does it buffer? There are memory limits set, and frames get thrown away when they are long time not used, and all that dynamic buffering stuff, which works pretty well. And even the replay timing with the millisecond settings get adapted when the first animation playthrough shows that it can just not be promised that GIF is running in the defined mode, which like in the file. So again, the important point is that this all can be done dynamically inside the primitive stuff, or alternatively in the renderer if you want. So that's the fourth example. You have questions for the fourth example? So maybe I still have the time to show the other examples. So
way over time.
Over time?
Show me something.
Yeah. So this, for example, is for fat line testing, just a lot of fat lines on, this is now on Windows, so I cannot show the optimization really, but this works now on Linux too. And just to show you the chart test, you can already come. I just want to show you the chart. The chart is now loading, and it will load for a long time, and at the end you get a little peek from the 3D rendering. So the 3D rendering and chart rendering is really optimized, but the chart data and the calc loading is really long and not parallelized. You see, this is a really big fat 3D chart, and this makes only a small peak with the software render.
Thank you, Ian.
Okay.
Woo!
Your turn.
Do we have an HDMI converter? That's the question.
Yeah, we do.
Yeah.